Hey, so I've read chapter one of Tom Mitchell's Machine Learning probably 6 times now. And I wanted to make a quick video to help myself really understand what's going on. It focuses on a simple example, teach a computer to play checkers against human players or to improve to be able to beat human players. And there's four key decisions you need to make. This is the intro of to machine learning. So there's four key decisions you need to make when designing a machine learning system, and I'll go through each one and try to explain it to teach myself. Number one is training experience. So we need to define how this machine is going to learn. So that could be represented a few different ways. It could be that there's a teacher that proposes certain board states in order to force the machine or the program to make decisions. It could be that it's watching human games. And the one that was chosen in this book is that it plays games against itself. That way, the amount of data is only limited, like it generates its own data, so it's only limited by what it can, like the time that it has. So that was the design choice that was chosen in the example. Number two is the target function. So the target function is basically what do we want this machine to learn? It could be a few different things. So if I scroll up here, it could be, so the one that they used in the example was, how good is this board state? How good are my pieces positioned to my opponent's pieces position? It could be, it could have been, what's the best move in this state? It could have been, what's the probability of winning from here? But the design choice that was chosen was, how good is this current board state? And that's the target function. And yeah, so if the board state is high, so for example, it could be it could range on values from 0 to 1. If it's high, maybe a 0.9, this tells the program, okay, this is a very good board state, you're likely to win. Yeah. So that's the target function. But then you need a representation of the target function, which is the third design choice. And the difference between the target function and the representation of the target function is that the target function is something in terms, it's what we want the computer to learn, but not in computer terms. So how good is this board state? A computer cannot understand what good means. So it needs to be representation of the target function, in an equation. The one that was chosen for this example was a linear function. Some of the features, namely x subscript 1 or x subscript 2, were, okay, how many of my pieces are on the board? How many of the opponent's pieces are on the board? How many kings do I have? How many kings does my opponent have? And the fifth and sixth feature were, how many of my pieces are threatened by the opponent's pieces, and how many of my pieces threaten the opponent's pieces. So representing that, you can do that by the set of integer or set of, it's not set of real numbers, whole numbers. So there's that. There's also in this, not each of those features are as important as the others. So the program needs to know, so it has weights associated with that, and it needs to know, okay, how important, is it more important that I have more kings than my opponent, or I have, or how many kings I have, or is it more important about my pieces that are being threatened? So it needs to weigh each of those, and that's all under the umbrella of the representation of the target function. And then a learning algorithm. So the learning algorithm, so you have your target function, which is what your machine, your program is trying to learn. Then you have a weight, basically a representation of that target function, something in a language that the computer can understand, to be able to arrive at what it thinks is that target function, because it doesn't know. Like, if you, whatever equation you come up with, that's not necessarily what's ideal. It's the closest approximation, but how can you for sure know the value of this board state is 65? You don't. So you try to get to an approximation as close as to what you think it is. So then you have the learning algorithm. And the learning algorithm is what determines whether the weights, how the weights should be adjusted, right? So if your program loses a game, based on the board states that were in that game, it's going to determine, okay, I should have given more weight to the amount of kings that I had versus the amount of pieces that were threatened. Because it needs a way to learn. It needs a way to adjust the current representation of the algorithm to improve, the current representation of the target function to improve. And two of the things that it, two of the or the way that was decided was it used least mean squares. So you take basically, that's tough. Let's see if I can explain that, because I got 7 minutes before I run out of time. So it used least mean squares, least mean squares. So you take basically the V train B. So you take the okay, so you subtract what the function, target function representation, eventual board state. So let's say I moved my red king to one space, right? Then my opponent takes a move, and then it's my turn again. It takes that successive board state, analyzes how much better that board state is than the one you just came from, and it subtracts the difference between that. So the difference between that would be an error, right? So if you, let's say you had a board state of 8, right? And then you make a move, and that board state is now 7. Your error was 1. You moved into a position that was less advantageous. I think I'm getting this right. So the least mean squares is going to penalize you by squaring. Oh, the squared error. So what's the difference between this? Trying to minimize, okay, the least mean squares tries to minimize the squared error. Yeah, I don't think I completely understand this. Okay, yeah, it's different. So the training values, it's trying to estimate what the training values are, and you take the board states, the successive board states, and subtract your current thought of what that is. So like, yeah, and then you square it. Yeah, and that's the error, exactly. So that's the error, and it's penalized, it's squared because it's penalized for more errors. Or you're penalized for egregious errors. Then the way that it updates the weights is that it takes what the program thinks the board state is, takes the future board states, so the board state after the move that it made, and subtracts the current board state and updates that by each weight, by each feature. So if you had let's say the feature of kings versus the feature of pieces threatened, and you moved one of the kings, and that's okay, I got through most of this, so I'm about to run out of time, but I think I explained more or less it somewhat well.